2019, and it will come to an end now at the end of this month. It's a project funded by the Interreg North Sea Region Programme, and we also receive match funding from the province of Antwerp, East Flanders and West Flanders. We are 11 partners participating and working together in 3 countries, being Germany, Denmark and Belgium. So for today, we have a program with different speakers. We will have a short break at 3:30. And I want to ask you, if you have questions during the different presentations, feel free to ask your question in the Q&A section of the Zoom. And then at the end of the webinar, there will be a short Q&A session, and then we will pick out some questions and we will answer them for the entire audience. Now, to keep this webinar light and digestible, we have also prepared a quiz where all of you can, of course, participate. We will ask 5 questions during our webinar. There are multiple choice answers. So besides trying to be correct, you also need to be fast, because the faster you can give your answer, the more points you can get. So if you want to join our quiz, then please take your smartphone or open an extra window on your PC. Then go to menti.com and enter the code which is shown here on the screen. Please don't close your Menti screen, because if you close it, you will be kicked out of the quiz and you cannot be the winner. So don't forget to keep it open at all times. And we really invite you to try to play and win, because we have a nice present for you. The winner will receive a box full of plants which are grown by a grower who applies a nutrient filter system. So sustainably grown pot plants. So I wish you good luck with the quiz, that the best can win. And we will immediately kick off with a first question, a question which will be asked by Hans Christian Hansen from the University of Copenhagen. So I invite you to watch a little movie.
Hello, I'm Hans Christian Hansen from University of Copenhagen. We work with filters for nitrate capture and filters for phosphorus, consisting of designed iron oxide coated filter material. I have a question for you. What is the lowest phosphorus concentration in surface waters that will initiate algal blooms? Is it 0.1 microgram per liter, or 25 microgram per liter, 100 microgram per liter, or even 1 milligram per liter? I look forward to your answer.
So I'm your quizmaster, I'm Nico. So you can now go to menti.com, fill in the code and start playing. We will wait a few moments to give everybody the chance to enter the quiz. People are coming. When I say start, you will see again the question, and then it will take 20 seconds, and then you will have multiple choice. I think we can start now. Here we go. And answer fast, because you get more points if you answer fast. Everyone has voted, so let's see what the results are. 8 persons got it right, and now we go to the leaderboard to see our first ranking after our first question. And then we see that Marianne de Bonne is in the lead, closely followed by Lore and Kees. So now it's time to move to our next speaker, and that's Bernd Lennertz from the University of Rostock. He's our keynote speaker. Go ahead, Bernd.
Yeah, good afternoon, everyone. Welcome. It's a great honor and pleasure to give this introduction talk here on the final conference of the NuReDrain project. We are jumping in. Let's see. Yes, there we are. The NuReDrain project is about nutrient removal from drainage water. And my introduction talk will focus in the first part on the nutrient loading of our coastal waters and our river basins. But I would also like to give a brief introduction into the relevant processes of the transport of nutrients from land to water, because that is important to understand what we can do actually to elevate the problem. So let's jump into it, and we can see here two maps of the northern part of Europe. We can see the Baltic Sea, and we can also see the North Sea. As we just have heard, the NuReDrain project has been financed by Interact and the North Sea region, so we have to look at the North Sea here. And these two maps show the integrated current and future eutrophication risk. The eutrophication is directly related to the nutrient input into waters, and it comprises algae blooms and, of course, the decay of algae and the oxygen that is required for the decay of the algae, and the according problem of the oxygen depletion in coastal waters, but also in inland waters. And we see the current situation on the left-hand side and the future situation on the right-hand side. And for the Baltic Sea, it is very evident that we really have a huge problem throughout the Baltic Sea. And it seems that the North Sea is entirely green, so no problem, but that is not true. If we are looking along the southeastern continental coast of the Northern Sea, we can see it is also affected. And of course, the coastal waters are affected because the rivers bring the nutrients from the land to the oceans. And behind this eutrophication risk is, of course, the nutrient input. We are looking here at nitrogen and phosphorus. So we have the same figure here for the North Sea coast, and we can see that along the coast we have higher concentrations of nitrogen that we have seen already in the other slide somehow. But what is more important is here the trend we can observe. And if we are looking at the recent years, let's say starting from 2006, we see that there is almost no trend. So the concentrations are not getting lower, but there's also no increase. So there's actually no change in the situation. And that is true for nitrogen, but that is also true for phosphorus, as we can see on this slide. Now, what is the reason behind that these nutrients are transported with our rivers to the coastal seas? It is, of course, the agriculture. Agriculture is here the main player. And this figure shows us the gross nitrogen balance in Europe by country. So what does that mean? What does nitrogen balance mean? It actually means the surplus of nitrogen we are applying to our agriculture field, surplus meaning more than the plants can take for their growth. So balance is a nice word for surplus, actually. And if we are looking or concentrating here on the three countries that are actually participating in the NuReDrain project, we can see, yes, there has been somehow an improvement in this surplus, but we are still taking the average of these three countries in the range of 100 kilogram nitrogen per hectare and year surplus. So, and that is actually one of the major problems. The temporal development of, again, nitrogen can be seen here. then again, it's the nitrogen surplus. And we are looking at the EU member states, and we see there was a peak of the surplus, and now there was an improvement, but it seems that now we have reached a certain high plateau of this nitrogen surplus. And that is somehow also reflected in measurements in water. So what we see here is the loading of the land because of agriculture practice. And here we see, as an example for Belgium, the percentage of monitoring stations, water monitoring stations, where the drinking water limit for nitrate, 50 milligrams per liter, has been exceeded. And it is interesting to see that there was an improvement in terms that less monitoring stations exceeded this limit. But over the recent years, the last year, again, there is an increase. And there might be several reasons behind that. It might be related to the input, but it might also be related to climate change. And I will come back to that problem later. So what we have seen is that there is a problem in coastal waters, but also in inland waters, of course. And the question is, will the nitrogen and the phosphorus that we put on agriculture, on our agricultural soils, will that end up in our water? And the question is yes or no. And the answer is yes. It's not yes or no, but it is more or less yes and no. Yes, because, and that is here, results from a very recent study published in Nature Geoscience, is if we relate this nitrogen surplus, here it is called net N input, with the loading of our river system, we can see clearly that there is a linear relationship, meaning the higher the surplus on our agricultural land, the more of this nutrient will pop up in our river system. So it is remarkable to note that more than 1/4 of this surplus will actually end up in the rivers. So yes, we can say at least a part of this surplus will end up in water. But the story is not that simple. And here I would like to show you a very, I would say, important study also published in Science a couple of years ago. And here we see the temporal development of the loading. In this case, it is the Mississippi River and the Gulf of Mexico. And what will happen if we are going to reduce the surplus. And we have two lines here. We have the green line. The green line indicates that would be the situation in the Gulf of Mexico if we are continuing agriculture as we did in the 1990s and 1980s. And the red line is where we want to go. This is the good ecological status of our waters, in this case, the Mississippi and the Gulf of Mexico. And what we can see, yes, if we decrease the surplus 25%, 75%, or 100%, we can improve the situation. But we will have to reduce the surplus to zero kilogram nitrogen per hectare and year in order to reach a good ecological status. That is the first thing we can learn here from this study. And the second, even more important thing is that it might take decades. It might take decades until we are there. Meaning, so if we are going to change something now, probably we won't see that for the next 10, 20, or 30 years. And that is also something we need to consider because we want to improve the water quality right now. So that is what we have learned, and this effect is called the legacy effect. The legacy effect is well known for phosphorus, And that is clear because phosphorus is strongly absorbed in soils and sediments. But nitrogen, especially nitrate, is mobile. And we would not expect such a legacy effect for nitrogen. But yes, there is, and this is strongly related, for instance, to the organic matter of our soils, because there is a complex nitrogen cycling in this organic matter. So now I want to jump into the processes, and we want to look at the processes with data from our field site. And you see our beautiful field site here is looks very natural. So the question is that what we are aiming at, the landscape that is all natural and very, not so much nutrient laden? No, it is of course not a natural landscape. What we see here is a brook that is straightened and deepened. Why is that the case? Because it is part of the artificial drainage system. And that is quite important. As we see on the next figure, we are looking here at the federal state of Mecklenburg-Vorpommern in the northern part of Germany, and we can see that more than 60% of the arable land is artificially drained, meaning that the entire hydrology of this land is modified and artificial to a certain degree. And the same is true for Belgium, the Netherlands, Denmark, and UK, etc., etc. So we have the same situation. So we have to consider this artificial drainage in order to combat nutrient surplus. And here we see our field site. So this is what we do not see in general. This is the systematic drainage system that is installed in 1 to 1 meter 40 depth. And the reason for that is to lower the groundwater table as indicated here in order to have heavy machinery on our soil. So that is the whole reason behind it. Now let's look at what we can observe at these areas where artificial drainage is, and we are looking here at a single field site. Now we see one winter period, so this is the rainfall on top, and the blue line indicates the discharge. And especially later in the winter or in early spring here, what we can see is that every rainfall event causes a discharge event. That is, of course, something we would expect. And there is a direct reaction. Immediately after rainfall, there is discharge generated. But what we would not expect is the also shown nitrate concentration. You can see the nitrate concentration is highly dynamic and it follows the discharge curve. And that is not what would we expect, because if there is high discharge, meaning there is a high volume of water, I would assume that a compound is diluted, but the opposite is true. It comes more the stronger the flux. And that is also something we need to consider. And we will see what the impact is of this situation. We can observe this, or we are observing this for more than 25 years on our field site at a single drain field. We are observing that here you can see the annual development that at larger scales and also at a very large scale. So that is the river basin of the Warnow River. So the surface area we are looking at is more than 3,000 square kilometers. And you can see that this relation is also true for this river basin. And there is a strong correlation between discharge intensity and nitrate concentration. So that is also something we need to look at and to consider. Okay, what we tried is to relate the surplus of nitrogen of this year with the according load in the water. Because I would assume, okay, we have a surplus, let's say of 50 kilograms, then I see like 1/4 of this 50 kilogram ending up in water. But no, we cannot relate the N balance or the N surplus to what we found in the water. We cannot relate that to the flow weighted mean concentration of nitrate here. Not from this year, not if we are looking at the balance of the last year, not if we look at the balance of the penultimate year. So this relation cannot be drawn. And that is, yeah, that is a problem for us who wants to improve the situation, to lower the concentration of nutrients in our waters. The only relation we found again is the relation between discharge and this concentration. So that is something we have to know. And what we see here is this effect, this legacy effect I've talked about earlier. Right, now this is also a very important study because it shows, for the example of the federal state of Mecklenburg-Pomerania, what are the dominant pathways for the nutrients. For nitrogen, there is no discussion. It is the artificial drainage system that is indicated by the red bar here, which is the dominant pathway. So if we want to do something, let's start at the artificial drainage system. The situation is a bit less clear for phosphorus because we have point sources for phosphorus, which are still important, like sewage plants, etc. But also for phosphorus, we can see, yes, the tile drainage system is an important pathway. So yeah, that is something we need to consider if we want to do something. Now, the climate change, I mentioned that also is somehow playing into our cards, we can say. We just recently analyzed the data for the Warnow River Basin, and what we found is, yes, there is an increase in temperature, in mean annual temperature, and there is more or less no change in rainfall. And what we see now, if we are looking at the load of the river, we see, yes, there is a decreasing trend in this load. And as seen by this red line and the red curve here, but it seems that the only reason behind is that we have less discharge, because the load is the product of the concentration and the volume flux of water. So if we have less water, we will have a minor nitrogen load. So, ladies and gentlemen, what can we do? In a landscape that is artificially drained, we have actually three options. We can lower the input of our nutrients into the system by reducing the surplus. Yes, I think that is something we have to do. We saw the figure. Only if we are reducing the surplus, we will have an effect in our water, but that may take a very long time. On the other hand, we can do two things. We reduce the flux. We reduce the discharge. You may ask, how can we reduce the discharge? Well, in an artificial drainage system or in a landscape that is artificially drained, we have access to these pipes, and we can have regulating units, and thereby we can regulate the discharge. In times of global climate change and high temperatures, that is also will come in focus, because we can hold the water in our landscapes if we are regulating these drainage systems. And the third option is we lower the concentration of the compound we are looking at. So number 2 and 3 are so-called end-of-pipe solutions. And these end-of-pipe solutions has been developed in the NuReDrain project. And this is what we are going to hear about. And this is something we need to do if we want to have an instant effect. So if I sum up what I have just said, is that we can see that the coastal waters, North Sea, but also, of course, the Baltic Sea is even more affected, are at risk because of this nutrient surplus. But this, of course, applies also to inland waters, because the inland waters brings the nutrient to the coast. And the nitrogen surplus actually controls the loading of our rivers, as we have seen but high concentration may be released for a long time because we have this legacy effect. And it is the hydrology which drives this export, right? So we have to look at this hydrology, and this is possible or accessible, let's say, in tile drainage landscape. And only end-of-pipe solution as developed and tested in NuReDrain have really an effect now, right now. And thus can accordingly contribute to ameliorate and improve the ecological status of our surface waters. Ladies and gentlemen, thank you very much for your attention. And I want to end with this nice figure of a wood chip bioreactor that we have installed in the frame of the NuReDrain project. Thank you very much.
Okay, thank you, Bernd. Then we come to our second quiz question. So for the participants who entered later, please know that we do a quiz during our webinar. You can go to menti.com and the code is shown on the screen. So if you want to join the quiz, still do so. And we will now listen to the question of Dominique Heuts from Inagro.
Hello, I'm Dominique Heuts. I'm working for Inagro. Inagro is a practical research institute for agriculture located in the western part of Belgium. Thanks to the NuReDrain project, we could test out 3 filters, an MBBR, a constructed wetland and a wood chip filter. Those filters reduce the nitrogen concentration out of drainage water. I have a question for you. Can you tell me what's the average obtained reduction of nutrients thanks to the NuReDrain filter systems?
So everybody can go back to his menti.com screen. When we have everybody on board, we can start the question. We wait a bit more. Okay, let's play the quiz. And answer fast because you get more points. The time is up and the correct answer was 60 until 80%. Let's now see the ranking after the second question. And Marianne de Bonne, who was in the first place after the first question, has now strengthened her position. She is now really leading with a quite large difference. Now it's time to go to the next part of our presentation. Also, we would like to remind you that there is a Q&A in the webinar. So if you would have questions about Bernd Lennart's keynote, don't hesitate to already write your question down in that Q&A section, and then we will answer that at the end of the webinar. And now we give the word to Pieter van Aken from KU Leuven.
Thank you, Nico. Hello, everybody. I am indeed Pieter van Aken from the Process and Environmental Technology Lab at KU Leuven. And I have the honor to introduce you into the different end-of-pipe technologies we applied in the NuReDrain project to remove nitrates from drainage water. And before we start looking at those technologies or those systems, I want to first highlight a little bit about the different water flows that we need to consider. We have a nice introduction of Bernd about the tile drained fields or the artificial drainage systems. That's of course the first type of water, and the drainage water, in which the concentrations vary between 12 and 50 milligrams nitrogen per liter. We have, yes, most of the time variable flow rates, and sometimes even really high flow rates that we need to treat. And yeah, because there's a link with the precipitation, of course, it's only during the winter. So from November until April, the drainage system, the water will come out of the drainage system. So yeah, that's only a part of the year that we need to treat that water. Also, because of the winter conditions, the water temperature will be relatively low. We measured minimum water temperatures of around 5 degrees, sometimes a little bit higher, 6-7 degrees. But even then, our technologies need to work, of course. And we are at, mostly we are at remote places, so electricity is not always available, where we that we need to take into account if we need to design a system to treat the water, of course. Besides the drainage water, there's also effluents from greenhouses, which contain a quite high amount of nitrate. Concentrations can vary between 25 and even 100 milligrams nitrogen per liter. But in most cases, the flow rates are much lower than when you compare it with drainage water. That type of water can come throughout the whole year. So, and yeah, most of the times we have indeed higher temperatures, even in the winter, because the water is coming out of the soil from a greenhouse. So it's a little bit higher in temperature, but that's not always the case. What are important considerations for designing a system? Because of course it needs to be a simple and a robust system. Simple because it should be easy to operate or to follow up or to maintenance by even farmers. It should be a robust system because it also has to work during winter conditions, for example, at remote places. We should be able to treat variable flow rates and at low water temperatures, and of course we want a low budget solution, but I think that's in most cases an important consideration to take into account. The filter systems that we applied in the NuReDrain project were all based on biological denitrification. Here you see the reaction, and indeed we go from nitrate throughout some intermediate products to nitrogen gas. And that's of course a drawback is maybe a difficult word to take to use, but yeah, it's a limitation of biological denitrification. Of course, the nitrogen, we cannot recover it. We also investigated a system in which we chemically try to do the reduction of nitrates into ammonia, but that was only at lab scale or first pilot scale tests. So yeah, I will not go into detail of that technology because it's in our point of view not ready to already install in real applications. So indeed, denitrification, what we need is a carbon source that's necessary to have a complete conversion into nitrogen gas. And you've seen that indeed one of the intermediate projects is a nitrous oxide. It's a green gas that's quite strong if you compare it with carbon dioxide. So it's important that we prevent the formation of this, of course, and therefore the carbon source is indeed an important parameter. You see also that pH can increase, but yeah, by defining a good carbon source or a good system, we can of course buffer that, and it should not be a big problem. Which are the different technologies that we have applied? First of all, a constructed wetland. The second is a wood chip bioreactor, and at last is a moving biofilm reactor. The constructed wetland and the wood chip bioreactor, at the beginning of the project, there was already some experience in Denmark. They showed some removal efficiencies for constructed wetland around 25%, for wood chip bioreactor around 50%. And of course, you want to make sure that we can reach those removal efficiencies or even improve them. The moving bed biofilm reactor, it was a new system that we developed specifically for areas where there's not a lot of space available to install such a big systems like a constructed wetland or a wood chip bioreactor. For those footprints, I will give some numbers later in the presentation. So first of all, what is a constructed wetland? It's more a natural system with 3 different basins, as you see on the picture. And between those basins, there is a kind of barrier, and within the barrier, some straws incorporated to use as carbon source. Those are the 2 pictures on the left. On the right, you see a different system where reed is used. It's more like a percolation reed bed, and it can also be another system, another natural system that can be used. What are the advantages? It's quite simple. So it can be operated by gravitation. No electricity is needed, and only limited maintenance. What are the drawbacks? That's the relative large surface area, and once the system is installed, no adjustments are possible. If we look at a wood chip bioreactor, it's a barrier structure, and it's used to lower the footprint. Therefore, we use wood chips, which will decompose and can be used as carbon source. So that's indeed the advantage, where we can reach higher removal rates, and therefore the footprint is much lower. But it still is a really simple system. And what are the limitations? Sometimes because of the decomposition of the wood chips, clogging can occur. And also there is a little bit of carbon release in the effluent, so you see a little bit higher of carbon concentration at the effluent. The moving bed biofilm reactor, there we use plastic carriers on which biofilm can grow. It's more an engineered system coming from industrial wastewater treatment. You see a concept on the picture below. So we use a drainage well to collect the drainage water. It's like a buffer. We pump it into the reactor, and to get some mixing, it's a little bit strange. We use aeration, and denitrification. Of course, you want to have low concentration of oxygen, but in this case, it was used for mixing, and we are able to keep the concentration low enough to have a denitrification. It's a really compact system, so we can reach very high removal rates. Think about the greenhouses, where it's necessary to treat high nitrate concentrations. And we are able to change some conditions to, depending on the situation of the water that we need to treat. Which are the limitations? We also have some carbon release in the effluent because we use an external carbon source. There is an increase of complexity, of course, and it's an engineered system, and we also need electricity for the pumps and the control and everything. The moving bed biofilm reactor, we made the main concept and we translate it into different applications depending on what was possible. So for the drainage water, it's are the two left pictures. So first an underground system where we use a concrete vessel underground, and then also some system for above ground within a sea container. And then on the right, you see to treat a greenhouse effluent, also an underground system. It's a similar one, but smaller than the one for drainage water. And then we developed something in cooperation with PCS. It's a do-it-yourself concept in which the farmer can build his own system for greenhouse, indeed. But I won't tell you anything about it because later in the webinar there will be some results of that system as well. Which lessons have we learned from all the field cases? First, from the development of the moving bed biofilm reactor, we were able to keep higher temperatures in the underground systems compared to the systems above ground, and that's most important in the winter. So in the above ground systems, sometimes we reach temperatures of 2 or 3 degrees, which is too low for denitrification. So there it was really difficult to have some activity. So we prefer to go underground. As carbon source, we need the external carbon source. We use glycerol-based carbon source because of the low freezing point. Otherwise, we have some problems in the winter as well when it freezes. And we noticed that if the mixing in our system is not good enough, we get some nitrite accumulation, and also the removal efficiency will drop. So we have learned also there that the mixing is really important, and yeah, it should be enough. For the operating costs, yeah, I show you some data from a system in Belgium. It's an underground MBBR of 15 cubic meters, and we followed it up for 3 drainage seasons. You see that the total treated drainage water, so the flow rate per day is quite the same. It's a little bit lower in the last year, but it's quite the same, and we were able to remove quite the same number of nitrogen. But when we look to the nitrogen efficiency, we see an increase every year, despite the fact that we lowered the amount of carbon source that we added. So the first year, we added 8.2 kilograms carbon per kilograms of nitrogen removed, but we lowered it with almost 50%. And we didn't see anything happening on the removal efficiency, and it even increased. So that's of course important that we see some changes during the year, and our biofilm is developing, is becoming more mature, so able to remove more nitrogen, even at lower amounts of carbon source that we added, and that has a huge effect on the operating costs. So it's also almost 50% lowering the operating costs. And also to maintenance, we noticed that regular inspection is necessary. So when we make a cost calculation, we keep it, we consider this indeed the labor or the amount of hours that's necessary. We also had a field cases in Roeselare. It's a cooperation with Inagro. They have a field of 7 hectares, and we collect all the water into the drainage pond. You see it on the above of the picture, and from that drainage pump, we are able to get water. We are able to pump water into the MBBR container. It's quite a small container, and 9 cubic meters of reactor. It has a footprint of 7.2 square meters. And Also, water from that pond is going to the constructed wetland. The constructed wetland has a footprint of 1,500 square meters. And at the end, you see also a wood chip bioreactor. There's two sections, the buffer section and then the wood chip section of 150 cubic meters. And the footprint in total is 370 square meters. That wood chip bioreactor is not connected to the drainage, to the pond, but receives water from a different field of 1.5 hectares. To show you some results, the constructed wetland in the last drainage season, this drainage season, was able to treat 2,000 cubic meters. The average incoming nitrate concentration was around 14 milligrams nitrate nitrogen per liter, and the outgoing concentration was below 2.2 milligrams nitrate nitrogen per liter. So the removal efficiency varies between 84 and 100%. And in total, this gives a total amount of nitrate removed around almost 30 kilograms nitrate nitrogen. If we compare to the wood chip bioreactor, it was able to only treat 324 cubic meters. The incoming nitrate concentration was a little bit lower, so only 7.18 milligrams nitrate nitrogen per liter, and the outcome nitrate concentration was approximately the same. So indeed, nitrate removal efficiency between 84 and 100%. And because of the low amount of water that has been treated, only 2.6 kilogram nitrate nitrogen was removed. And then eventually the MBBR, it has treated almost 7,000 cubic meters. It receives on approximately the same concentrations as the constructed wetlands. That's of course logical, because approximately the same water was coming from the pond, and the outgoing nitrate concentration was higher than the other systems. It was 7 milligrams nitrate nitrogen per liter. So the removal efficiency was only 53%. In total, the MBBR was able to treat almost 50 kilograms nitrate nitrogen per liter. That's of course of the high amount of the water that has been treated. When we look to the cost efficiency, we made a cost efficiency where we take into account the investment cost and the operating costs. You can see that the constructed wetland and the MBBR are quite the same, where we need to mention that the MBBR is a little bit underdimensioned, resulting in a little bit higher nitrate effluent concentrations. It's not able to treat that high amount of drainage water. And the same for the wood chip bioreactor. You see a really high cost efficiency. That's because the system was overdimensioned. The system was too big for that amount of water. So it's a really high investment cost, but you only treat a small amount of water. So in the three cases, we have comparable cost efficiencies. On cost efficiency, the systems can be are competitive with each other. To come to a conclusion, I try to come up with a decision tree. You don't need to take it absolutely, but it's given a direction when to use which system in which situation. First of all, is it tight drain field or is the greenhouse? If you go for a greenhouse, is the available area large enough, or are the concentrations relatively low? Then a percolation reed bed can of course be used. I don't show any results of that, but we also investigated that in the NuReDrain project. So we have some results available. If it's not, we will advise you to use an MBBR. If it's a tile drained field and you have quite a lot of area available, you can go for a constructed wetland or a wood chip bioreactor. Is there a restriction of the amount of area available? Yeah, consider to go off-grid or not. Is it possible to use electricity or not? If no electricity is available, if you're at a remote location, use the wood chip bioreactor. Can you use electricity? Then go for an MBBR, of course. So now we are at the end of my presentation. Thank you for listening, and I have the opportunity to introduce you to the movie of Bjarne for the quiz, of course.
Hello, I'm Bjarne Stobel from University of Copenhagen. We are working with filters to remove nitrogen and phosphorus from drainage water, and I've got a question for you about the capacity. So filter materials can be used to retain phosphorus from water, and the question is, how much phosphorus can typically be retained with 1 kilo of filter material?
So if everybody can take his smartphone or go back to his Mentimeter window, we can now play our third question. We will wait a little bit. So here we go with the question. Everyone has voted. Let's see what the results are. Only 2 persons were right. And have a look at what that means for our ranking now. Simon scores very well and means he is running up to the 2nd position, but Marianne de Bonne is still in the lead. We can now continue with our presentation, and I want to give the word to Junwei Hu from the University of Ghent for his presentation. The floor is yours, Junwei, and you have to unmute yourself.
Yeah. Hello, this is Junwei. I'm from the Department of Environment at the Ghent University. In this part, I will show you our work about phosphorus removal from agricultural drainage water. This research is carried out together with the colleagues from NuReDrain. So currently, there's low efficient management practice to reduce phosphorus leaching on the shorter term. In Northwest Europe, an important share of agricultural land is drained, and this drainage water is a concentrated source of phosphorus discharge directly into the surrounding water. Therefore, there is a large mitigation potential to reduce the phosphorus discharge at the end of the drains. So, for this purpose, we developed a filter to absorb the phosphorus. In the lab, we tested different filter materials, and we found the iron coal descent showed highest capacity of removing phosphorus. And this is because the iron could form a chemical bond with phosphorus. And the iron coal descent is a waste product from the water industry. So it also caused no other contaminations. So using this material, we developed a phosphorus filter. So the drainage water goes inside the filter box and first go down and then move upwards, have a contact with the iron coated and then discharged. So when the flow is higher than the capacity of the filter box, the water could directly discharged. We installed several this prototype filter box in the field, and we evaluate the performance for long term. Let's have a look about the result. So at the site of Zethem, we have 3 filters there, and now I will show 2 of them. One filter has been installed for 5 years. From this table, we see the phosphorus removal efficiency. The y-axis indicates the volume-weighted phosphorus concentration, and the bars indicating the dark blue bar indicating the total phosphorus at the inlet, and the light blue bar indicating the total phosphorus at the outlet. And the dark green indicates the dissolved reactive phosphorus at the inlet, and the light green indicated this the dissolved reactive phosphorus at the outlet. We test the phosphorus. We test performance for 5 years, from 2018 until this year. So 5 drainage seasons. Below the year, we can see the range of the flow. So at the first year, we could see the phosphorus were almost removed, but the remove efficiency becomes a bit lower with the time. But still, at the end of the 5th year, the phosphorus filter box still showed relatively high phosphorus remove efficiency. And this is also the case for the other filter we tested for 4 years, also at Zethem. So at the first year, almost all the phosphate were removed, and still at the 5th and the 4th year, still more than 60% of the phosphate can be removed. However, not every site showed very good results, and we think it is because of the flow. We further investigate the dissolved reactive phosphorus remove efficiency and the flow. From this graph, we can see the axis is the flow rate, and the y-axis is the dissolved reactive phosphorus remove efficiency. So the phosphorus remove efficiency decrease with the flow increase. And this is just because with flow increase, the reaction time decreased, and also sometimes the overflow occur. So generally, we can say if the flow is below 0.2 cubic meter per hour, which is 4.8 cubic meter per day, we could achieve a relatively high phosphorus efficiency, like around 50%. So currently, the filter box is placed in the ditch, but ideally the ditch should not be obscured. So we further tested to bury the filter box at the edge of the field inside the soil. And we did 2 of them. And both are at that stadium, and the installation proven to be relatively easy. How about the performance? Yeah, because the first year, both 2 filters showed very low phosphorus concentration, so we did not show the data. At one of the filter in the second year, the phosphorus concentration is high, and we only look at data with the flow rate lower than 4.8 cubic meter per day. At this flow rate, the phosphorus filter showed around 50% remove efficiency for the dissolved reactive phosphorus. As we can see from the previous graph about the flow and the remove efficiency, our filter cannot treat bigger volumes of drainage water. So to achieve this, we designed another upscaled filter box. So this filter box is two cylinder elements. In between of them, 140 liter iron coated descent was filled. And this filter element is placed in a cubic container. How does this filter works? So first, the water is pumped to the center of this filter elements, and then it goes from inside to outside, goes through the iron coated descent, enter the cubic container, and then discharged to the ditch. We have two of these upscaled filter box installed, one at a collector drain at the Belgium coast Middelkerk, and the other one at the open pond of Inahro. We test these filters for 2 drainage seasons. The first year at Inahro, the phosphorus concentration is low, but the second year, the phosphorus concentration is better, is higher. And we managed to have a good result. So again, the dark blue is the total phosphorus at the inlet, and the light blue is the total phosphorus at the outlet, and the dark green is the dissolved reactive phosphorus at the inlet, and the light green is the dissolved reactive phosphorus at the outlet, and the y-axis is the phosphorus concentration. So at the average flow of 8.8 cubic meter per day, we achieved 75% of the dissolved reactive phosphorus remove efficiency. But however, we constantly got problem with the open pond water. Yeah, it's a clogging problem. So to prevent this problem, we installed a pre-filter. But still, we need frequent maintenance to ensure the optimal water flow. However, the upscaled filter does not working so well at the Middelkerk. So at the first year, the phosphorus remove efficiency is around 20%. And we further improved this filter to reduce the flow and to make sure the whole elements is used. But still, the phosphorus remove efficiency is not increased in the second drainage season. We assume this could be due to the water property, but still need to be confirmed for further investigation. In the end, we compare the cost of these two types of filter box. So the small filter box is based on the 3 filters at Zetterham, tested for 3 to 5 years. So averagely, every year, 150 cubic meter of water is treated. And at the average phosphorus concentration of 0.14 ppm, with average phosphorus remove efficiency of 72%. So every year, 14.3 gram phosphorus is removed. And the cost for 1 kilo phosphorus remove is 1,750 euro. The upscaled filter box is calculated based on the upscaled filter at Inahro, tested for 1 year. So at the average flow rate of 8.8 cubic meter per day within the drainage season of 4 months, so we estimate 1,000 cubic meter water being treated, and with the incoming phosphorus concentration of 0.21 ppm, with the average phosphorus remove efficiency of 75, we estimate 166 grams of phosphorus was absorbed. And then with 1 kilo of phosphorus being removing, it cost 1,500 euro. Yeah, compared to the lead treat, it's much more expensive, but it's also because our phosphorus concentration is much lower, and I suppose if with a higher concentration, it could be cheaper. Yeah, so in conclusion, our research provide a low-tech solution which showed high phosphorus remove efficiency, but a relatively low cost of the filter material and does not cause under contamination. But there are also some limitations need to be solved. The first, the peak flow could result in low remove efficiency for the small filter box. And the clogging problem need to be solved for the open pond water. And the water property may hinder the phosphorus removal at some site. Yeah, that's all of my presentation. Thank you for listening.
Okay, thank you, Hunwei. There is no question in between Hunwei, his presentation, and mine, so I continue. My name is Els Powels. I'm working at the ornamental plant research here in Belgium in Destelbergen. And we learned a lot of Peter about the MBBR and N filters. We learned already some things about the P filter of Hunwei. So what we thought is, what can we install 2-in-1 filters, P and N filters, together to have a total removal of N and P. So the N filters that can be constructed, wetlands, wood chip filters, and MBBR, and the P filters, there were in first several possibilities of filter material, and that the NuReDrain project helped us to find which filters can be the best filter for which condition, in fact. So something that is very important is for growers, in fact, certainly, is that they have to keep reusing as much water as possible. The water that we are treating, certainly for the greenhouse growers, is surely only for the water that is not reused, because reuse is a priority. So you can gain fertilizer use by 30%. So and also the water is so important now, so that reusing is really a priority. But if you then have wastewater, and in greenhouses that's mostly max 5% of the total amount of water, then we have some filters constructed that we can lower the N and P concentrations. Something that is also important and sometimes forgotten is that pesticides, rests of pesticides, are not removed by our filters. It's really N and P filters. If you want to remove the pesticides, then you still need another filter, which is a biofilter. If you want more information about that, we had also some projects on it. So we have a lot of experience also with biofilters. And what we learned also is that in the MBBR, Peter told already, there is a biofilm which is created. And therefore, it's important, if you have a 2-in-1 filter, to put first the P filter and then later the N filter. Otherwise, on the material of the P filter, there will be also a biofilm which will prevent the working, a good, efficient working of the P filter. So, yeah, we have chosen for the ICS grains, as Hunwei already said, but therefore we did a lot of research. It was a team of Peter and Nico who did a lot of research on many different filter materials. Also at Vito, they tested a lot of filter materials to know which filter material can be used in which condition. And there were more than, finally we resulted in 11 filter materials where we did a lot of research on, and then we diminished them to 4 good materials that can be used. But indeed, ICS is something that is very easy to use because it is a waste product from the drinking water production, and it has really it can really absorb very well the P. Then it has the disadvantage that it's desorbed less good than on other materials, but it can absorb very good the P material of the P, and therefore you can have a high conductivity in the filters. And till now it's sufficiently available. But we tested also at PCS other materials. We have also the pellets. That's pellets that are made from the sludge, also from the drinking water company. But yeah, that's an extra step that they have to do with the sludge. So currently now it's not available anymore, but you will see in the results that it is certainly as good as the ICS grains are. Good material, but a bit a problem of the availability. And then we have other materials like Vito A and Vito B that are also materials based on iron coated set, the Vito B iron, and on aluminium, on the Vito A. Materials that work very well, we will see it. And then later in the project, we also did test with the regenerated ICS, which later on Jeff will talk about. And you have seen the material from Hunwei, which was tested in the field. They have very low concentrations of P. And we were thinking, oh, when they are saturated for the filters in the field, can we still use them for us for the greenhouse filters? Can they be still useful? And these are results, for instance, for last year. And there you see in orange, but you don't see any orange on the figure, also only here a little bit. It were new ICS, that's important. The results, the P at the inlet is the blue bar, and so the orange bars are the P at the outlet. When you have new ICS grains, even with high loads of P, it works really very good. For greenhouse water, we have, of course, the advantage. Yeah, it's a high load, then you have pretty good efficiency. And we don't have any problem. It's clean water from the greenhouses. We don't have any problem with clogging and so on. So these are advantages to have such a good result. Our pellets, unfortunately, they were saturated. They are here already for more than 5 years, and we couldn't replace them with new because they were not available at the beginning of the season, because we only started beginning of June. You see that they still work, but they are saturated so fastly they don't work anymore. And here we stopped the filter after August. That is something that we always see in the beginning of the season. The P, it's something funny, or not funny, but it's something that we see, that the P is going deeper into the grains, and there are new possibilities to absorb at the outside of the grain. So they are, even if they were saturated last year and you let them acquire some time, then when you again start up your filter systems, they work again in the beginning. But of course, they are again fastly saturated. The other products, Vito A, Vito B, and the product and the product that we received from Hunwei, they worked very well in the beginning, but they were only very small amounts, max 5 liters. And after a while, of course, they were saturated. We knew this would happen, but they are really also very good materials. Even the material of the field, in the beginning, it works very well. But then they were saturated. And this is the same for the regenerated ICS. It worked also in the beginning very well, but at a certain moment, of course, it was saturated. Winter conditions don't have really an impact on the P filter. So, and then we have a 2-in-1 filter. We have a P filter and a second filter. We chose for the MBBR because that's very compact and easy. Like Peter already told you, we need a carbon source for this and an aeration pump, but in fact, and the carriers, but that's almost everything. So it's really easy to install. And therefore we have a demo unit that we show to the growers. And we have also demo moments where we show how it works. And we made a manual, which is available in Dutch and in English, of how you can make your own MBBR. So it's simple and compact. How much water can we process? We process till 3 cubic meters every day. It's robust, cheap, and there's no recovery. The carbon source, well, 5 to 8%, yes, sometimes, but on another side, we needed to go up to 15%. So it really depends on the water that you are treating, how much carbon you have to add. So that's something that during using it, something that you can still have to adapt. And the P filter always works very well in winter, but in the N filter, in winter times when it's freezing, then it can be difficult in operation. The efficiency can be lower then. So we tested different 2-in-1 filters into practice, and this is the grower that you saw in the beginning, where the winner of the quiz will receive the plants of, and he was one of the really first growers to be interested in these P and N filters. Why specific for this grower? Because he grows potted plants that are really susceptible to a particular bacteria, and therefore reusing his water is sometimes difficult. Sometimes he has to discard his water, and he can do that on his grassland, but therefore he can only put certain amounts of water on that grassland. And if the N and P concentration of the water is lower, then he can add more water per square meter. So therefore, first he has his N and P filter, first only a P filter, but later on also an N filter. So he can put more amount water per square meter. And he has a floristry with potted plants, and he has 750 cubic meters drain water a year. And at the start of the project, we first have the 2P filters and then the MBBR filter. So also there we treat 3 cubic meters every day. And you have also an aeration pump into the in the MBBR, which is running 20 times a day, only 1 minute. And here we see some results of his P filter. So there we made the mistake of having first the MBBR filter and then the P filter and seeing, oh, the biofilm is really over our ICS grains having a layer, and it doesn't work anymore so good. So there we had to switch. But after the switch, which was in 2021, I think, after the switch in 2022, everything worked well again. So you see here the P at the inlet and then the P at the outlet. And even in December, it's working very well. The MBBR, that only started here in July. So this is a start. It couldn't work yet here at that moment. This is a start before. But then we had very good diminishing of the N during the season. But for instance, in December here, we had no, it didn't work. December was rather cold. The average temperature in December was 4 degrees. So it is outside, and then you can have some difficulties. It's not under the ground like the system of Peter. There you have a better control of the temperature. And now we are going ahead. More and more growers are interested in having these 2-in-1 filters. That's something that is also typical after a lot of years of research. At the end of the project, the growers are become more and more interested and want to install these systems. For instance, this grower is an azalea grower, and there is one greenhouse that he the water can't reuse because it's an old greenhouse and it's somewhere apart from the other. So he can solve his problem now thanks to our filters. And this is a typical what we call 2-in-1 filter. So first you have the P filter at the left. There are in fact 2 cubic containers, and then the MBBR in between the carbo, ST, the carbon source, which you need for the MBBR. The water is collected in a buffer tank. It's pumped into the P filter. It goes up, and then it goes into the MBBR, and then it's at the outlet. Normally we can treat 3 cubic meters, but here it was only necessary to treat 1.5 cubic meters. But if necessary, we can have a higher inlet. Another greenhouse where a 2-in-1 filter is installed is a greenhouse with young plants. It's a very big company, this. They grow orchids, Phalaenopsis and Helleborus mainly. So they have young plants and they reuse all their water. But what is treated then by us, it's their backwash water from the multimedia filter and also the cleaning of the tanks. So they have a lot of wastewater, but they have also a constructed wetland and another P filter. So it's only a part of their amount of wastewater that we are treating, only almost 1 cubic meter. If they would want to treat all the water with our system, then you would need a filter that is 3 times as big as this one. But that's installed also last year and is now up and running. And then the most recent filter that we installed is also drain water from a greenhouse with azalea. Also here, there is a UV filter to reuse all the water, but the backwash water can be pretty much. Here it's for one backwash, it's 1.5 cubic meters. And if you have more than one backwash, for instance, 2 backwashes each day, then you can treat all this water with the NNP filter to be able to lower the concentrations. So here you can see the total installed installation. What is the cost of a two-in-one filter? Well, let's say that the cost for the P filter is mainly pumps, the cubitainer, and nowadays, before we just received the ICS from the drain water company, but nowadays you go buy another company and you have to buy the ICS grains. So it comes now up to 1,000 to 1,500 euros for a P filter. And for the MBBR, which is a little bit more complex, and you need energy there, we say it is up to 2,000, 2,500 euros. So in total, a two-in-one filter system is 3,500 up to 4,000 euros that it costs. But efficiency, certainly for the P filters here, we have really efficiency for greenhouse water, 80 to even almost 100%. The MBBR is more around 70% efficiency that we obtained. So, and this is my last slide. I really want to thank my colleagues, Marijke, Bruno, and Bram, who did most of the practical work.
Okay, thank you, Els. Then we have come to our break. It's about 3:30. We would stop for 15 minutes. So please stretch your leg and take something to drink. And we will start again at 3:45. Now, in the meantime, if you have some spare time, I invite you to complete a survey that we launched. It's already posted in the chat. It's a survey to know from our participants if you have made use of the NuReDrain project results. Have you used our output material? Did you construct a do-it-yourself filter, and so on? So it would help us to know who made use of it, and it's also important for our Interreg final report. So thank you in advance if you complete the survey, and we meet back again in 15 minutes. Thank you. Okay, welcome back again. We will move on with our webinar. We have 2 more presentations, but before that, let's go for another quiz question. And the question will be asked by Bart Michielsen from Vito. And here it is.
Hello, I am Bart Michielsen from Vito, where we investigate the reuse of saturated P filter materials. I have the following question for you. P needs to be removed from the water because it's causing eutrophication. But does it also need to be recovered from the filter material and be reused?
So everybody can go back now to their Mentimeter screen and prepare themselves for the 4th out of 5 questions. We'll go to menti.com again. Okay, we will start now. Remember, answering fast gives more points. Here is the question. Okay, we have 4 correct answers. And the correct answer is yes, phosphorus removal is necessary to enable filter material reuse. Now look at our scoreboard. And we can still see that Marianne de Bonne is in the lead quite comfortably. That looks very nice for Marianne. We can now move to the next presentation. And we have Jeff Bergmans from Vito, who will give a presentation on regeneration of filter materials.
Yeah, good afternoon. Jeff Bergmans from Vito indeed. I work in the waste recycling technologies team there. And together with my colleague Bart, that you have seen in the quiz, we have worked on developing new filter materials. As you have seen in the presentation of Els, there was Vito A and B there, made from drinking water treatment sludge. But the presentation I will present today will be on the regeneration of used sorbents. What we did first in the project is check if we could actually use these sorbents directly as a phosphate source in pot trials. That would be a nice option. We use them as a substrate in pot trials or in agriculture, and then they release the phosphorus that is available. Now, we did see though that the phosphorus that is sorbed on the sorbents is very attached to the sorbents, so it's not readily available to the plants. And even if we use phosphorus solubilizing bacteria in combination with these iron-coated sand, this loaded iron-coated sand, we still not achieve the same as when we add a phosphate nutrient. So this route was abandoned because of not very promising results. The other routes that we were looking at then is to at least regenerate the sorbents. So in literature, you see 2 routes to recover the phosphorus from the sorbents. There is the acidic route and an alkaline route. The difference there is mainly that in the acidic route, indeed you recover more phosphorus than in the alkaline route. But the issue is that you also start dissolving a lot of the actual sorbent. And so if you see at the capacities of these sorbent, then you see that only a few grams of phosphate is actually sorbed on a kilogram of sorbent. So we decided, and it's also economically more interesting, to focus on the filter material recovery to make sure that the filter material is not completely destroyed, and to have a more selective removal. With the alkaline route, where we basically replace the sorbed phosphorus by hydroxyl groups on the surface of the iron hydroxides or oxides. There is already some literature available on this, but most literature works on very small scale experiments and also tests performed on artificially loaded sorbents. So we had the availability of sorbents that came from the fields, and that was more interesting because also there you will see more also loading in the inside of the iron-coated sand. So very shortly, what did we do? We desorbed with potassium hydroxide. Why potassium hydroxide? It's a bit more expensive than, for instance, sodium hydroxide, but potassium is a nutrient also in agriculture. So this would mean that the resulting solution that we get, because the phosphate would come in solution, that we could still use this solution in agriculture. If we would have a lot of sodium in this solution, this would of course not be feasible. And then we wash the desorbed sorbents with sulfuric acid. Why do we do that? First of all, after treatment with potassium hydroxide, the sorbents have a very high pH. Of course, if we want to make sure that the water that we treat afterwards it's feasible to just discharge in, for instance, surface water, we don't want a pH of 12.5, because that's also not good environmentally. So we need to get a neutral pH again. Second of all, by doing this, we might dissolve some potential precipitation products. For instance, calcite, calcium phosphates could, during the alkalinization, could precipitate and block some of the sorption sites. We started with small scale lab tests, but we did upscale to bigger scales. We also didn't see any issue from going to bigger columns. And the column you see here, that's 12 kilogram of material. That's a column that we used to treat the material that we sent back to PCS, and that was once again more tested as a sorption material. So it worked well. As El said, it's not a lot of material, so you can also not use it a very long time, 12 kilogram, but the results were promising. If we look back in our results, and we see that we can desorb phosphorus from the saturated ICS grains, that the type of base alkaline solution has not a big influence. So we used both potassium hydroxide and sodium hydroxide in the beginning. We went to sodium hydroxide, potassium hydroxide for the nutrients, and that we can keep on recirculating the alkaline solution. That you also see here, we basically recirculate the same solution over the column, and we keep the pH at the pH of 12.5, where we keep on adding a little bit of potassium hydroxide the longer the experiment runs. We then do the opposite. Afterwards, we add an acid and bring the sorbents back to neutral pH. And with that, we managed to absorb 8 to 9 grams of P per kilogram of sorbent, which is basically what was sorbed before. So almost all P that was sorbed we can desorb in this process. And then you see these are the sorbents after desorption that were sent back to PCS to reuse in a different setup. Well, if we use a higher alkaline concentration, we get, of course, we remove more P. But if we use too much, we go too high in pH, then of course we start dissolving also more iron of the surface. And so we cannot go that high in pH to make sure that the integrity of the sorbents is still there and that we can keep on reusing. Ideally, we would have a few sorption-desorption cycle. And that's then it's of course important that the integrity stays stable. Now, what we also did is we looked in the technical economical assessment what is more economically interesting, to just buy new sorbents and landfill the old ones, or to desorb them. So we assumed that there was already a sorption setup available. We assumed that the loaded sorbents would then be landfilled. That's at the moment we think the only option. Of course, if loaded ICS or loaded other iron oxide-based sorbents, you find a better solution for them besides landfilling, then that cost will disappear. And then for the desorption case, you have to invest, of course, in a desorption setup. You can use the same setup that you use for the sorption column if you have used material that can withstand a high pH. If you use steel in your sorption setup, then the high pHs that we would use would cause rust. So you ideally work with material like polypropylene or PTFE and so on. You also use a peristaltic pump or a chemical pump that can again withstand the high pH. And you need a steering system, basically a pH meter and a feedback system that basically says, if your pH drops too low, to add extra potassium hydroxide. Then you also need to, of course, pay for the potassium hydroxide and the sulfuric acid. And the nutrient solution that we get could be used for plants because it basically contains potassium, sulfates, and phosphates. So that's all useful nutrients. We did not take into account, however, the price of this nutrient solution. So we just assume you can use it, but we didn't give a positive value to this solution yet. And those things we've put in a tool that will be available on the NuReDrain website, where you can also adapt the yellow cells. And so, I mean, the data we've put here, that's based on the research within the NuReDrain project. But for instance, if you find cheaper sorbents, or the landfill cost in your country is different than the one in Belgium, or the lifetime of your sorbents is longer, then you can adapt this, and then in the end you will see the price difference for desorption. So if this is green, it means it's better to desorb. If it turns red, it means it's better to just buy new sorbents. This will also depend on how big your installation is. If you only have an installation of, let's say, 10-20 kilogram, then it's maybe not worth to start with all desorption setup. If you have an installation, in this case, of 1.5 ton, you see that it starts being worth investing. And that was my last slide.
Okay, thank you, Jeff. Then we move on to our last quiz question. So if you still want to beat Marianne, be quick and be correct. So it's a question asked by Marijke Dirks from PCS.
I'm Marijke Dirks from PCS Ornamental Plant Research. We test two-in-one filters to remove nitrogen and phosphorus from greenhouse effluent. I have a question for you. The cost for nutrient removal depends on the concentration of nutrients in the water and the volume of water to be treated. What is the average cost, investment and operation for a moving bed bioreactor?
So please everybody return to manti.com and we can play then our final question. Okay, I will press enter to start the quiz. And answer fast, as Charlotte said, will give more points. Everyone has voted. There are 5 correct answers. And indeed, it's between 100 and 1,000 euro per kilogram nitrogen removed. So now we are coming to our final ranking and we will know if Marianne has won the quiz. Let's see. What did Marianne answer? Okay. And the winner is indeed Marianne de Bonne has won our quiz competition, Charlotte. We want to invite also Marianne to unmute the quiz. Her sound. We will allow her to talk. Marianne,
hello.
Hi.
Hello, Marianne. Well, congratulations, you are the
Thank
winner.
you.
Can you perhaps briefly introduce yourself? Where are you from? From which organization? From which country?
I am Marianne de Bonne. I'm from Belgium. I'm working at the Department of Agriculture and Fisheries, and I'm working on the manure and fertilizer policy.
Okay, so
and I'm very happy.
Yeah, well, you did well, and you are of course very much involved in this topic, but your knowledge is up to date, I would say. So congratulations.
Thank you.
So as announced, you will receive a parcel with pot plants, which are grown by Goderic Meuning. It's a grower in Nevelen in Belgium, and he has a 2-in-1 filter system to remove his nitrates and phosphates. So we are happy to offer you this. So if you just can send me an email with your postal address, and then we will make sure you will receive it.
Okay, thank you.
Yeah, good luck.
Bye.
So that was it for the quiz. We will now move on to our last speaker, Andreas. Andreas, you have the floor.
Yes, hello everybody, and also congratulations from my side to Marianne. And I am also from Rostock University, and the work I want to present today is a joint work together with Bernd Lennertz, who had the first presentation, and now I'm the last speaker of the official part of this meeting, I would say. The title of my presentation is Different Scenarios for Nutrient Removal in a Catchment. And I want to introduce the application of the cost evaluation tool. So our study catchment is the Warnow River Basin, which is located in northeastern Germany at the Baltic Sea, and it has a size of about 3,000 square kilometers. And if we look on the nitrate concentration data in this catchment and in the different sub-catchments, which you can see on this figure on the upper right, you see large differences between the individual subcatchments. Here you see annual mean values from 1990 until 2017, and you see very comparably high concentrations for the subbasin Beeke and very low concentration for the subcatchment Mildenitz. What is the reason for this? The reason for this is clearly the proportion of agricultural land in these subbasins. We have the highest load. Here you see this in the lower left picture. You see we have the highest nitrate load in the subcatchment of Beeke, where we have a proportion of arable land which is more than 75%. In contrast, the proportion of arable land in the Mildenitz subbasin, which is the green dot and which corresponds also to this green line here above, where we have a lower proportion of arable land. What does that mean? And also we have in the last 30 years a weak decreasing trends. But if we want to install end of pipe solutions, which we have heard today a lot of, then we should focus on hotspot subbasins, which is in our case in the Warnow River Basin, the Beeke subcatchment. So let's have a look on this so-called hotspot catchment. You see here a map of this subbasin. This catchment is about 30,000 hectares in size, and all the green areas are artificially drained. This is approximately 50% of the subbasin area, and also you can see on this map red and blue lines. The red lines are pipes and the blue lines are open water. And the annual nitrate nitrogen load in the subbasin is approximately 352,000 kilograms, which corresponds to 12 kilograms nitrate nitrogen per hectare and year. And what is important, we have here, according to this map, 435 polygons, which means individual drain plots, according to this map. So what options do we have to reduce the nitrate load with the help of technical solutions? It was already mentioned that we could install, for instance, moving bed bioreactors, or we could install wood chip filters, or another option would be the installation of constructed wetlands. We have heard also a lot of the investment and operational costs of these different systems. And we also have heard about the different efficiency of this systems. So the main study questions here were, what is the nitrate removal potential if we would install these filters at a catchment scale, and what are the annual costs? To answer this question, we developed a cost evaluation tool, which I want to introduce right now, and I want to give you some examples how you could work with the tools or what the results could be. So the tool is in fact an Excel file. which was developed to easily predict the nutrient production reductions and costs due to the implementation of technical end-of-pipe solutions in artificially drained catchments. We need some input data, which is the drain plot area. We also should know the mean annual water flow and the mean annual solute concentrations, which could be nitrate or phosphorus. We should estimate the filter removal efficiency and also the costs in euro per kilogram solute reduction. If we have all these information, we get the following output data. We get the actual loads. Okay, this is easy to calculate. This is just the concentration times the discharge, as Bernd already mentioned. These are future loads after we installed the end-of-pipe solutions. These are the reductions. The units are always kilogram per year and also kilogram per hectare in year. And it's the cost in euro per year for the entire considered catchment and in euro per hectare and year. And the output data will be calculated both for individual drain plots and for the entire catchment. These data can also visualized. They will be visualized in the Excel file itself, and the spatial data, for instance, the drain plots are shown in an integrated QGIS project. Here you see a screenshot of this tool. We developed 3 different settings, and this is the so-called advanced settings, where you can define the area of the drain plots where you would like to install MBBRs or wood chip filters or surface flow constructed wetlands. You can define a minimum annual nitrate concentrations in which filters should be installed, and also you can you define the costs per kilogram solute reductions for the 3 different systems, and also you can define, here it is named the reduction target, which is in fact the performance of the filter. So, and here you see some different figures, and here you see the start of the tabular data. So I want to come to a first example, which is related to the basic settings, if you want to start to play a little bit with the tool. So first, we should define the boundary conditions. As I already mentioned, in the Beke catchment, we have 435 drain plots, and we assume that they have the same discharge and nitrate concentrations. And Bernd already mentioned our experimental field site, where we have long-term data, and the average data here is 168 millimeters per year in discharge and nitrate nitrogen concentrations of 9.6 milligram per liters. So let's assume that the drain plots in the Beke catchments have the same discharge, have all the same discharge, and have all the same nitrate nitrogen concentrations. Filters will be installed at all 435 drain plots, but the performance and the costs per kilogram nitrogen reduction vary. So what is the result? Here you see two different figures. On the y-axis, it's always the filter performance, and on the left-hand figure, on the left-hand side, you see the nitrate nitrogen load as a function of the filter performance. And of course, you see that the nitrate nitrogen load decreases independent of the filter performance, and also in opposite, the nitrate nitrogen load reduction in percent increases accordingly. So that means assuming a filter, just to give you an example, assuming a filter performance of 50%, the nitrate load in the catchment can be reduced by 35%. As you see here on the right figure, you see that the total cost depends strongly on the cost to reduce 1 kilogram of nitrate. So here we see total cost of approximately 2 million euro per year until 12 million euro per year. Anyway, the total cost will exceed 1 million euro per year in each scenario. Let's come to another example. Let us assume this is more, I would say this is more reality, because not every drain plot has the same annual discharge, and also the nitrate concentration vary. So let us assume, to take realistic values, the annual discharge of the drain plots is between 80 and 150 millimeters per year, and the nitrate nitrogen concentrations vary between 3 and 15 milligrams per year. And let's say we implement filter technologies only in drain plots where the mean annual nitrate concentrations are larger than 10 milligrams per liter. And let's say the MBBR, they should preferred installed in small sized drainage plots, smaller than 2 hectares, at costs between 115 euros per kilogram N reduction. And the wood chip filters should be installed in medium-sized drainage plots from 2 to 10 hectare at costs of 2 to 20 euro per kilogram N reduction. And the constructed wetlands, they should be installed in large size drainage plots of larger than 10 hectares at costs of 5 to 95 euro per kilogram N reduction. And also, let us assume that the removal efficiency of these systems vary depending on the drainage plot, depending on the locations, and there are many other reasons why the removal efficiency vary. And let's say these removal efficiency vary between 30 and 90%. So, all the mentioned values will be randomly selected in the given ranges, and we did in total 100 runs. And here you see the results. Depending here on the left box plots, depending on the scenario, the costs will probably between 2 and 3 million euro per year for the entire catchment of the Beeke. And the nitrate, what is interesting, the nitrate load will be reduced by approximately 15%. And And also according to these scenarios, the filters will installed at circa 117 drain plots, 30 MBBRs, 60 wood chip filters, and 80 surface flow constructed wetlands. When we look on the lower box plots here in this figure, we can say that the surface flow constructed wetlands will be most expensive. No, you see this here. Here you see the costs in €1,000,000 per year. Wetlands will be most expensive, but they will consider the largest area, which you can see here, and they will be therefore the largest driver to reduce the nitrate pollution here in this scenario. Okay, I have a last example how to visualize the data. Let's say we want to implement the constructed wetlands at drain plots with a nitrogen load of more than 15 kilograms per nitrogen and hectare, and in an area of in drain plots that are larger than 10 hectares. The boundary conditions are again annual discharge is 80 to 150 millimeters per year, and the nitrogen concentrations are between 3 and 15 milligram per liter. Let's say the performance of the constructed wetlands is 50%, and the costs is €30 per kilogram nitrogen reduction. The aim of this example was to visualize the drain plots that all fulfill the criteria and to visualize the expected costs. And here you see the result. You see the map of the sub-basin Beke, and we could identify 39 out of 435 drain plots that fulfill the criteria, and the costs vary between 226 and €331 per hectare and year. The total cost in the entire catchment is approximately €1 million per year. So I want to come to a conclusion, and an Excel-based cost evaluation tool was developed to calculate nutrient reductions and filter costs using hotspot catchment as an application example. And we can conclude the following. Due to many hardly predictable costs and necessary simplifications, single calculations are mostly to be understood as rough estimates. I think this is very important. Therefore, scenario analysis using multiple calculations, only they can provide a realistic range of expected costs and nutrient reductions that policymakers and stakeholders can work with at the watershed level. And our results suggest that filter systems, if installed widely in the landscapes, can help a lot to reduce the nutrient pollution in surface waters significantly. However, as you already saw, the installation and the maintenance of filter systems can be very costly. That means that filter systems will always be side measures and will not replace the necessity of sustainable agricultural systems. They can support other measurements, but they are, of course, not the only ones to reduce the nutrient pollution in our agricultural used landscapes. What I forget to mention is, if you want, all of you, I would invite to test the cost evaluation tool. This is freely available. You can download it from our website, and it comes together with the QGIS, project, and also with the manual that guides you step by step, that you know how to work with this tool. So feel free to use this tool. Thank you very much, and I am open for questions. Thank you.
Okay, thank you, Andreas. Indeed, then it's now time for our Q&A session. I will stop sharing. We did receive some questions in the chat and also in the Q&A section, but please, if you still have questions, feel free to put them. But I will already handle some questions. A first question is for Peter. So Peter, you explained that there are different nitrate removal systems. We have the constructed wetland, the MBBR, and the wood chips filter, for instance. Now you also explained that the conversion from nitrate to nitrogen gas involves an intermediary step where there is the production of nitrous oxide. And now the question is, should you take into account these emissions to actually decide which system you want to use? And have you ever made a comparison between these systems based on the N2O emission?
Yeah, okay. The N2O emission, to measure it, it's not that easy. We haven't done it in the project, but it's indeed something important that we need to take into account, of course. But we already know that there is a link between nitrite and the emission of nitrous oxide. So yeah, in that way, we already know more or less what is happening. So indeed, we measure the nitrites as well. And that's why I told in my presentation, there was an increase of nitrite. We have some accumulation of nitrite, where we assume that there will also be an increase in emission of nitrous oxide. So it's something we have to do indeed. But if you compare it with biological treatments in industrial wastewater or in communal wastewaters, those measurements are now, or the topic is now increasing in interest. So it's something that we need to do, but we are not able to compare the different systems based on that criteria at this moment.
Okay, thank you for your answer. Then we move on to the next question, which is for Els. Els, the question is, how long will a P filter applied on greenhouse effluent will have a good P removal? When do you need to replace your ICS grains?
Mm-hmm. Yes. Yeah. Replace the ICS grain. We want to regenerate it, like Jeff showed us how, but it will depend, of course, of the load of the P, how long it will take. At our site at PCS, I must say there was an average of 10 milligrams P in the water that we treated. Then we could hold during 5 years the same ICS grains, but we didn't treat in the winter. So it was from April till October every year. And then we could keep them for 5 years. At grower side, we see that goes quicker. For instance, a grower that uses the whole season, even in winter, then it can be 3 years, something 2-3 years, depending on the load. With high load, it will be 2 years and otherwise 3 years. And then we hope that we don't have to replace them. but we can regenerate them and use them back again.
Okay, clear. Then I have another question, which is for Andreas. Andreas, a drainage system can be dry, more in the summer months. Will a wood chip reactor then still work?
No, no, because in summer, a wood chip reactor will not work in summer because there is no water flowing through the wood chip filter. But we have installed a wood chip filter in 2017. So in every year, so the wood chip filter falls dry in summer, and then the season again starts in November. And then the wood chip filter works again and very properly. That is absolutely no problem. So in this year, for instance, the discharge season ended in our case exactly at the end of April. So this was quite normal. But in November it starts again and it works.
Okay, so the bacteria remain somewhere alive to do the job. Yeah. Okay. Then I have a question for Bernd. Sorry, when you see the lights, it's a train who is passing here. Yeah. Bernd, is it possible that the relation between a high nitrate concentration in the drainage water and a high quantity of rainfall is due to the use of artificial fertilizers that dissolve better in humid conditions?
Yeah, thank you for the question. I think that refers to the slide I have shown where we saw similar behavior of discharge and concentration. And we have to remember that this is the winter period. And I would assume that the farmer is not applying any fertilizer in winter, better not. I mean, he or she is not allowed doing so. So the figure I've shown can actually only be explained if we assume that the storage of nitrogen in the soil is more or less endless. Because if it's only the discharge driving the export, then it can only be explained if we have a very high storage of N in the soil. And we also know that it's the molecule we apply, the molecule of fertilizer we apply on top of the soil, the probability that we will find that exactly molecule down in the drain pipe is not very high, because that is incorporated into the organic matter of the soil and other substances, and then is at a later stage again mineralized. So the proportion of fertilizer that is directly transported downwards is minor, and I would say in the range of 10% or so. So it is actually very complex, but if we have extraordinary events in summer, which we have in the recent years, where we have 100 millimeters and more of rainfall within 24 hours, we will even see discharge in our drainage system in summer because of this extraordinary high event. And then if the farmer has applied fertilizer before, there's a very high risk of transport, not only for nitrogen, but also for phosphorus. And then we might see extraordinary high peaks of phosphorus and nitrogen.
Mm-hmm. Okay. Then I have a question for Peter. It is related to your slides about the Godelieve fields. The question is, what surface was serviced with the 3 systems?
You mean the total drainage area?
Yeah, the drainage area for the MBBR and the constructed wetland versus then the drainage area for the wood chips.
Yeah, so the drainage area for the MBBR and the constructed wetland was 7 hectares in total. the water was collected into the pond, and from the pond we pumped it up to the MBBR, and it was flown gravitational to the constructed wetland. And then the Uchi bioreactor, it was on the other side of the field, and there it was, the total drained area was 1.5 hectares. Yeah.
Yes, okay. And then there is a last question. And we all saw that the price for NNP removal is still quite high. If you express this in euros per kilogram of N or kilogram of P that needs to be removed. And then the question is, who will pay for this? I think it's a question we can all answer a bit or not. It's a difficult question, but I will take it for myself, because at the end of the project, we tried to find a suitable business model so that we can achieve the implementation of these filters in the field. So we have talked to, for instance, farmers organizations, to auctions, to processing industry, to drinking water companies, to local, regional, and national authorities to discuss on how we could facilitate this, because it's clear that we need to improve the surface water quality. It's also clear that filters can help, but who is to pay for this? So I will come to this in a minute, because we have come to a sort of solution, and I will briefly tell it in the concluding remarks, which I will start now right away. I will go back to the slides and take the last 10 minutes of your time to conclude this project, and to also look a bit to the future. So what can we say from our 6 years project? What are take-home messages? So we have demonstrated with our field cases that the installation of nutrient filters can remove nitrates and phosphates out of agricultural waters, and as such, it can improve the surface water quality. However, there is no one-fits-all filter solution. It all depends on the flow that you need to treat, on the concentration of nutrients in your water, on the availability of electricity or not, on the water temperature, on particles, and so much more. So you need to make a tailor-made solution which is suitable for your case. And we tested several filters, and I hope that at least one filter can be suitable for a problem in your catchment. We also found out that the amount of P that can be recovered is limited. Today, it's not economically feasible to recover the P because it's just too small amounts. But we do hope that if there is a massive implementation of these filter systems, then we will really have bigger quantities, and from then on, it can make sense to go for P recovery. And then last, we could also demonstrate that regeneration of the P filter material is possible and can also be desirable. It can be cheaper to regenerate it than to buy new material. Now, all of our project results are gathered in several outputs. We have created project videos. So if you want to learn more about the different field cases, different filter systems, then take a look to our different project videos. We also created fact sheets. These are 2-pager documents which describe the working principle of the filters and the advantages and the disadvantages. So also take a look at that. There is a do-it-yourself MBBR construction manual. It explains the working principles of an MBBR. There's a dimensioning tool with it, and there's also a guide which tells you step by step how you should start building a do-it-yourself MBBR. Then there is a cost evaluation tool, as Andreas explained. This will tell you for a catchment which systems could be installed at nutrient hotspots and what would be the corresponding investment cost. You can also do what-if analysis, so you can really set your own boundaries to find out where you should invest at first. Then there is also a P-filter material regeneration tool. So Jeff explained you if you want to find out for yourself if desorption of saturated P-filter material is useful, then apply the Excel sheets and find it out for yourself. And then all of our results have also been described in scientific articles and in field case descriptions. So there's a lot to find out, and there's one single point to find it. That is our website. So please have a look if you need further information. Now, we also asked the farmers' opinion about our filters, and they confirmed that they are looking for a simple technology which requires not too much space. They are willing to invest in it, but of course it cannot be too costly. They agree with costs of something less than 5,000 euros. They are open to do investments within 2 to 5 years. Some farmers prefer individual measures, so they just want a filter system on their own parcels. Others prefer collective measures, so they would then combine different water streams and install one collective filter. And in the case of collective measurements, they would like to contribute to the price for that collective measure based on a fixed price per crop. Now, we have come to the end of the current NuReDrain project. We have not yet a follow-up project. We are, however, open to it. So if any of the participants would like to cooperate with us and has bright ideas, be my guest to contact us. But the focus for now is that we want to go to an implementation of the filters in practice. So to really have a replication of our field cases at many other locations across Europe. And to stimulate this, as I explained you, we looked for a suitable business model. And I'm very happy that the Flemish government in Belgium decided to support nutrient filter systems. So as of the 1st of June, farmers who invest in a filter system can receive 75% of public support coming from European means through the Common Agricultural Policy. So who will pay for it is somehow answered with this fact. And I hope that I'm very happy with the decision that was made in Flanders, and I hope it can be of inspiration also for other countries, so that we can, as a kind of social responsibility, strive for a better surface water quality. We also launched a survey, as I explained during the break, to all participants of our different webinars to ask, have you used the NuReDrain results? Have you consulted our manuals? Have you installed filters? And the results received so far showed that there are already 30 do-it-yourself filters somewhere out in the field. The survey is anonymous, so I don't know where these filters are, but if you want people who completed the survey, you can always send me a message and let me know where they are. Then what we would like to work on for the next coming years related to the application for greenhouses, we would like to have an on-site filter material recovery system so that it goes automatically. We remove phosphates and nitrates, and then there is like kind of automatic regeneration of your filter material, and you can just continue. So that would be a nice application from point of view of PCS. And then, of course, we also want to focus more and more on the phosphorus recovery. As I said, it's not economically viable yet, but we do think SP is a critical element, that it will be more and more relevant in the future. With that, I want to conclude this webinar. Yes.
I'm sorry, but there are two questions, I think, in the Q&A that we didn't answer. We answered the questions on the chat, but
okay,
not on the Q&A before you really end.
Okay, yes. So then we go back to the Q&A.
There's one new question, actually, Charlotte,
yes,
from Jonas van Egem.
Yeah, so I will read it out loud. To use such a nutrient filter system, is there always an artificial drainage system necessary under the agricultural land? And how much of Belgian agricultural land has such drainage systems? I don't know who is willing to answer this, perhaps Els or Peter, at least from Belgium.
Yeah, I can't answer. I don't have the info.
Peter, sorry, I was just now thrown into the question.
Yeah, I don't have an answer on the amount of Belgian agricultural land that has been using such a drainage system. I only know that it's applied in a lot of cases, I think, but that's my opinion. But I can't give any number. Yeah, if it's necessary that the nutrient filter system can only be used, it's not necessary, but yeah, if almost all agricultural land is using artificial drainage systems, then it's quite logical that we are using the tile outlets to install our filters at. That's the place where you collect it, but of course it's not necessary. You can collect it in a ditch and then try to treat it. So yeah, it's not really necessary, I think.
Okay, and I see that John Ray in the meanwhile is also typing an answer. I can also tell you, so in Belgium, we don't have maps of, let's say, of drained areas, but let's say it's around 60 to 70%. And as Peter explained, you could as well treat runoff water, but the biggest volumes will come through the artificial drainage system. So it would be good to connect it to this, I would say. Okay, I hope this answers all the questions. If there are any other questions remaining, feel free to drop an email and we can still answer it later on. But then to really conclude, I want to thank the entire project team. Thank you for your commitment, your enthusiasm, and your expertise during these past years. We have met a lot. We have met a lot in the fields, sometimes in the sun, more often in the rain, but it was always a pleasure to be together. And with that, I also want to thank the Interreg North Sea Region Programme for the financial funding, the province of Antwerp, East Flanders, and West Flanders for the match funding. This webinar has been recorded, and together with the slides, the recording will become available on the website later on, and you will then receive an email with a link. So thank you all for your attention, and see you at a later moment, I would say. Thank you. Bye-bye.